block of mass 2.1 kilograms is sitting on a frictionless ramp with a spring at the bottom that has a spring constant of 405 newtons per meter. The angle of the ramp with respect to the horizontal is 11 degrees. Part A, the block starting from rest slides down the ramp a distance 31 centimeters before hitting the spring. How far in centimeters is the spring compressed as the block comes to momentary rest? The gravitational force moving the mass is mg sine theta. So the work done by that mass, or by that force, will be mg sine theta times L, the 31 centimeters, plus mg sine theta times x, the distance the spring is compressed. Remember that gravity is still doing work as it compresses the spring. The sum of those two works will equal the energy stored in the spring, 1/2 kx squared. Now we have to solve a quadratic because we've got a constant term, a term with x, and a term with x squared. We get two solutions. We want the positive solution. We get 8.783 centimeters. Part B, after the block comes to rest, the spring pushes the block back up the ramp. How fast is the block moving right after it comes off the spring? 1/2 kx squared is the energy we have stored in the spring. We have 1/2 mv squared kinetic, but we're also moving it up the ramp the same amount as it moved down the ramp before, mgx sine 11 degrees, because we want the velocity when it leaves the spring. So we put these in, we solve for v, and we get 1.076 meters per second. Part C, what is the change of the gravitational potential energy between the original position of the block at the top of the ramp and the position of the block when the spring is fully compressed? We know the distance it moved along the ramp is the initial L, 31 centimeters, plus the x that we found above, 8.78 centimeters, or 0.3978 meters. The change in height is that length times sine of 11 degrees, or 0.0759 meters. So the change in potential energy is mg delta H, or 1.56 joules, and it's negative since it moved to a lower potential energy.